In December 2025, astronomers announced something remarkable. Using the James Webb Space Telescope, they had observed a world unlike anything ever seen before. A Jupiter-mass planet orbiting a pulsar, one of those rapidly spinning neutron stars left behind when massive stars die. A world squeezed into the shape of a lemon by unimaginable gravitational forces. A place where the atmosphere contains no water, no methane, no carbon dioxide, none of the familiar molecules we associate with planets. Instead, this strange body is wrapped in helium and carbon, dominated by molecular carbon in forms called C2 and C3 that exist nowhere else among the roughly 150 planetary atmospheres we have studied. Soot clouds drift through its alien skies, and deep within its interior, those carbon particles may be compressed so intensely that scientists believe they form diamonds. The planet, officially designated PSR J2322 2650b, completes an entire orbit in just 7.8 hours. It races around its stellar companion at a distance of only about 1 million miles, roughly 1/100th the distance between Earth and the Sun. When the research team first analyzed their data, their collective response was simply this: what the heck is this? And here is the thing. This discovery, as bizarre as it sounds, is not the exception in our growing catalogue of alien worlds. It is becoming the rule. The more we look into the darkness beyond our sun, the stranger the universe becomes. Hot Jupiters that orbit their stars in mere days, super-Earths that have no equivalent anywhere in our neighborhood, planets made of diamond, planets covered in lava oceans, planets that rain glass sideways in howling 1,000 miles per hour winds, 6,080 worlds. That is the official count as of mid-January 2026. 6,080 confirmed planets orbiting other stars in our galaxy, spread across more than 4,500 planetary systems. And with each new discovery, a question grows louder in the minds of astronomers around the world. A question that cuts to the very heart of our existence. Where are the solar systems that look like ours? If you are enjoying this journey through the cosmos, consider subscribing to the channel and leaving a like. Your support helps us continue exploring these wonders together. For most of human history, we assumed we were ordinary. Scientists called this assumption the principle of mediocrity, a philosophical stance suggesting that Earth occupies no special place in the universe. We live on an average planet, orbiting an average star in an average region of an average galaxy. The cosmos, this thinking held, must be filled with billions of worlds much like our own, countless solar systems arranged in patterns similar to what we see when we look up at our own familiar sky. It seemed reasonable. It seemed humble. It seemed for a very long time to be correct. But as these recent discoveries have reminded us once again, the universe cares nothing for our assumptions. Consider what we have learned in just the past few weeks. That lemon-shaped world orbiting its pulsar is just one example. Also in December 2025, the James Webb Space Telescope detected the strongest evidence yet for a thick atmosphere surrounding a broiling super-Earth named TOI 561b. This world orbits its star so closely that its year lasts less than 11 hours. Its surface is covered by a global magma ocean, a sea of molten rock that glows with the heat of a furnace. And yet, against all predictions, this tiny world appears to have held onto a substantial atmosphere, a blanket of gases that no one expected to find on such a scorched and tormented body. The researchers were surprised. The prevailing wisdom had been that small planets orbiting so close to their stars simply cannot maintain atmospheres. The stellar winds, the intense radiation, the sheer violence of being that near to a nuclear furnace should strip away any gases within millions of years. TOI 561b breaks those rules. It forces us to reconsider what we thought we knew about how planets form and evolve. And then there is the discovery of WASP 107b, a giant planet caught in the act of losing its atmosphere in spectacular fashion. The Webb telescope observed enormous streams of helium gas trailing behind this world like the tails of a cosmic comet, extending nearly 10 times the planet's radius. It is not just that this planet is evaporating. It is that the escaping gas actually precedes the planet along its orbital path, a phenomenon that has forced scientists to rethink how atmospheric escape works on worlds beyond our own. These discoveries share something in common. They all describe planets that are profoundly different from anything in our solar system. And this pattern, this endless parade of alien configurations, has become the defining surprise of exoplanet science. Let us step back and consider what we expected to find when we began this grand search for worlds around other stars. For centuries, the only planetary system humanity knew was our own. 8 worlds orbiting a single yellow star. 4 small rocky planets huddled close to the warmth of the sun. 4 giant planets, vast spheres of gas and ice, orbiting in the cold outer reaches. An asteroid belt between Mars and Jupiter. A scattering of icy bodies beyond Neptune. Everything arranged in nearly circular orbits. Everything spinning in the same direction. Everything confined to a thin disk, like the grooves of an ancient record. This was our template. This was what we thought the universe would show us. The first confirmed exoplanet around a sun-like star was discovered in 1995. It was a world called 51 Pegasi b, and it shattered our expectations immediately. Here was a planet with roughly half the mass of Jupiter, a genuine giant world. But instead of orbiting far from its star like Jupiter does from our Sun, 51 Pegasi b raced around its stellar parent in just 4 days. 4 days. It was so close to its star that its atmosphere was heated to over 1,000 degrees. A hot Jupiter, a type of planet that simply does not exist in our solar system. Scientists had to invent a new term to describe it. And that invention was just the beginning. In the 3 decades since that first discovery, we have found thousands more worlds. The Kepler Space Telescope alone discovered over 2,700 confirmed planets and thousands more candidates. The Transiting Exoplanet Survey satellite continues the search today. Ground-based observatories scan the skies with ever more sophisticated instruments. And what this combined effort has revealed is both wonderful and deeply strange. Hot Jupiters turned out to be fairly common, at least around certain types of stars. But they are just one flavor in a vast menu of planetary weirdness. We found warm Neptunes. We found mini-Neptunes, planets larger than Earth but smaller than Neptune. A size category that has no representative whatsoever in our own solar system. We found super-Earths, rocky worlds, several times more massive than our own planet. Super-Earths, remarkably, appear to be among the most common types of planets in the entire galaxy. And here is the critical point. Our solar system contains no super-Earths. None. Not a single one. Think about that for a moment. The most common type of planet in the Milky Way, a category of world that apparently forms readily and frequently around other stars, is completely absent from our cosmic neighborhood. It is as if someone made a list of the top 10 most popular car models in the world, and you discovered that your entire country had never manufactured or imported a single one of them. A study published in 2023 by researchers at the University of Bern and Geneva examined hundreds of planetary systems and classified them into 4 distinct architectural categories. They called these categories similar, ordered, anti-ordered, and mixed. In similar systems, the planets all have comparable masses, like peas in a pod. In ordered systems, the masses of the planets increase with distance from the star. In anti-ordered systems, the opposite is true, with the heaviest planets closest to the star. And mixed systems show chaotic variations in planetary mass from one orbit to the next. Our solar system falls into the ordered category. Small, rocky worlds close to the Sun, giant planets far away, a sensible progression from small to large as you move outward. And according to the data, this ordered architecture is the rarest of the 4 types. The researchers found that approximately 80% of all planetary systems have similar architecture, with neighboring worlds of comparable size orbiting at regular intervals. Our solar system's arrangement, with its dramatic jumps from tiny Mercury to enormous Jupiter, with its clear separation between rocky inner worlds and gaseous outer giants, appears to be genuinely unusual. This finding adds to a growing body of evidence that has accumulated over the past decade. In 2021, a separate study by researchers at the Niels Bohr Institute in Copenhagen examined more than 1,000 planetary systems and found a clear mathematical relationship between the number of planets in a system and the shapes of their orbits. Systems with more planets tend to have more circular orbits. Systems with fewer planets show more elliptical, elongated paths around their stars. Our solar system, with its 8 major planets and their remarkably circular orbits, fits this pattern. But here is what makes it strange. The average eccentricity, that is, the degree of elongation in an orbit, for exoplanets with orbital periods greater than 5 days is around 0.23. The Earth's orbital eccentricity is 0.017. Venus has an eccentricity of 0.007. Neptune comes in at 0.009. Our planets trace nearly perfect circles around the Sun. Most exoplanets do not. Most exoplanets follow stretched elliptical paths that would look quite different from the gentle loops of Mercury and Mars. Why does this matter? Because orbital stability is connected to orbital shape. A planet on a highly elliptical orbit will experience dramatic variations in temperature as it swings close to its star and then far away. Its seasons would be extreme, its climate chaotic. A planet on a circular orbit, by contrast, receives a more consistent amount of energy from its star throughout its year. Its climate can stabilize. Its temperatures can remain within ranges that allow liquid water to persist on its surface. Liquid water, that substance we consider so essential to life as we know it. The circularity of Earth's orbit is not the only unusual feature of our cosmic home. Consider our position within the Milky Way galaxy itself. Our solar system orbits the galactic center at a distance of approximately 27,000 light-years. This places us in a region called the Orion Arm, a minor spiral arm located between the larger Perseus and Sagittarius arms. We are not at the center of the galaxy, where stars are packed so densely that gravitational interactions would regularly disrupt planetary orbits. We are not on the outskirts, where the raw materials for building planets, the heavy elements forged in the hearts of dying stars, are scarce. We occupy what scientists call the galactic habitable zone, a ring-shaped region where conditions are thought to be most favorable for the development of complex life. Too close to the galactic center, and a planetary system faces frequent supernovae, dense stellar encounters, and intense radiation from the supermassive black hole that lurks there. Too far from the center, and the ingredients for making rocky, water-bearing planets become increasingly rare. But here is what makes our position even more special. Our Sun orbits the galaxy at nearly the same speed that the spiral arms themselves rotate. This means we rarely pass through those dangerous regions of star formation, those dense lanes where supernovae are common and radiation levels spike. We drift along in the quiet suburbs of the Milky Way, protected by our velocity from the most violent neighborhoods. Even among stars within the galactic habitable zone, our Sun is somewhat unusual. Approximately 75% of all stars in the Milky Way are red dwarfs, small dim stars with masses less than half that of the Sun. Our Sun is a G-type main sequence star, sometimes called a yellow dwarf, a stellar category that makes up only about 3 to 7% of all stars in the galaxy. Red dwarfs have their own potential for hosting habitable planets. The TRAPPIST-1 system, for instance, contains 7 Earth-sized worlds orbiting a red dwarf star, only 40 light-years away. But red dwarfs present challenges that our Sun does not. They are prone to violent flares that can strip away planetary atmospheres. Their habitable zones are so close to the star that any planets there would likely be tidally locked, with one hemisphere in perpetual daylight and the other in endless darkness. Our Sun is stable. It has low luminosity variation, fluctuating in brightness by only about 0.1% over its 11-year solar cycle. No solar twin has yet been found with an exact match to this remarkably steady output. This stability allows Earth's climate to remain relatively constant over long periods, a condition that may have been crucial for the development of complex life. The numbers are beginning to tell a story. Rare orbital architecture, rare stellar characteristics, rare galactic location. Each factor considered alone might not seem so significant, but together they paint a picture of a planetary system that departs from the galactic norm in multiple ways simultaneously. And we have not yet discussed the giants. Jupiter is the largest planet in our solar system, a world so massive that all other planets combined would fit inside it with room to spare. It orbits the Sun at a distance of about 5 astronomical units, 1 astronomical unit being the distance between Earth and the Sun. Saturn follows at about 9.5 astronomical units. These 2 worlds, the twin monarchs of our outer solar system, may have played a crucial role in making Earth habitable. The Grand Tack hypothesis, proposed by planetary scientists in 2011, suggests that Jupiter did not always orbit where it does today. According to this model, Jupiter formed closer to the Sun at about 3.5 astronomical units, and then began migrating inward through the young solar system. It drifted ever closer to our star, pulled by the swirling gas and dust of the protoplanetary disk from which all the planets were born. If this migration had continued, Jupiter would have spiraled all the way in to become a hot Jupiter, incinerating or ejecting any small rocky worlds that might have been forming in the inner solar system. Earth would never have existed. But Saturn came to the rescue. As Saturn formed and grew, it too began migrating inward. It caught up to Jupiter, and the 2 giant planets fell into a gravitational resonance, a mathematical relationship between their orbital periods that caused them to interact in a specific, predictable way. This resonance reversed their migration. Instead of continuing to fall toward the Sun, Jupiter and Saturn began moving outward again, eventually settling into orbits similar to where we find them today. The term grand tack comes from sailing, when a sailboat changes direction dramatically to catch the wind from a new angle. It is called tacking. Jupiter tacked. It reversed course at about 1.5 astronomical units from the Sun, roughly the current orbit of Mars, and headed back out into the cold. This cosmic near-miss had profound consequences. Jupiter's inward journey scattered much of the material in the inner solar system, limiting the amount of rock and metal available to build planets. This is why Mars is so small. There simply was not enough material left in its region of the disk to build a larger world. And this is why our solar system has no super-Earths. Any planetary embryos that were growing into super-Earth-sized bodies were either ejected from the system or pushed into the Sun by Jupiter's gravitational influence. Saturn saved us, in a sense. Without Saturn, Jupiter would have kept falling inward. Without Jupiter's reversal, the inner solar system would have been swept clean of the raw materials needed to make Earth. But here is the catch. This grand tack scenario requires a very specific configuration of giant planets. It requires Jupiter to form first and grow large enough to migrate. It requires Saturn to form at the right time and in the right location to catch up. It requires the resonance between them to trigger outward migration before Jupiter had a chance to reach the inner planets. And it requires the gas disk to dissipate at just the right moment to freeze the giant planets in place. When we look at other planetary systems, we rarely find this kind of arrangement. Many systems have hot Jupiters, suggesting their giant planets migrated all the way in. Other systems show giant planets on highly elliptical orbits, suggesting chaotic gravitational interactions that scattered them wildly. Still others have no giant planets at all, leaving their inner planets exposed to the full bombardment of comets and asteroids from the outer reaches of their systems. Only about 10% of Sun-like stars appear to have giant planets like Jupiter and Saturn, and of those, even fewer have those giants in stable circular orbits at the proper distances to protect an inner habitable zone without disrupting it. Our solar system's giant planets are not just large. They are precisely placed, and their influence extends beyond simply sculpting the early solar system. Jupiter continues to affect the cosmic environment today, though its role is more complex than the simple shield hypothesis that was popular in previous decades. The traditional view held that Jupiter acts as a cosmic vacuum cleaner, using its enormous gravity to attract comets and asteroids that might otherwise strike Earth. The spectacular impact of comet Shoemaker Levy 9 into Jupiter in 1994 seemed to confirm this idea. Here was visible proof that Jupiter could absorb dangerous projectiles. But recent simulations have painted a more nuanced picture. While Jupiter does deflect some long-period comets, sending them out of the solar system before they can threaten Earth, it also appears to redirect certain asteroids and short-period comets onto more dangerous trajectories. Jupiter is both shield and slinger. It protects us from some impacts, while potentially increasing the risk of others. What matters most may be the overall configuration. A system with a Jupiter-sized planet on a stable circular orbit in the outer regions appears to provide a net benefit, reducing the most catastrophic impacts while allowing smaller ones that may have actually been important for delivering water and organic materials to the early Earth. But change the parameters, move Jupiter closer or farther, give it a more elliptical orbit, remove Saturn from the equation, and the delicate balance collapses. The inner planets either get bombarded into oblivion or stripped of their protective conditions entirely. This is the emerging picture of our solar system. Not an average collection of worlds, not a typical arrangement of planets, but a specific, perhaps rare configuration that happened to produce the conditions we now take for granted. Circular orbits, a quiet galactic neighborhood, a stable sun, giant planets that migrated just far enough and then stopped. An absence of super-Earths that might have disrupted the inner system. A single, modest-sized rocky world in the habitable zone with enough water to form oceans, but not so much that it became an endless water world. How rare is this combination? That is the question that haunts exoplanet researchers as they sift through the data from Kepler and TESS and the James Webb Space Telescope. That is the question that echoes in the silence of the cosmos, in the absence of any signal from extraterrestrial civilizations, in the puzzle known as the Fermi paradox. If solar systems like ours were common, we might expect the universe to be teeming with technological civilizations. The galaxy is old enough, and the ingredients for life appear to be everywhere. And yet, when we look up at the stars, we see only silence. When we search for radio signals from other worlds, we hear only static. When we send messages into the void, there is no reply. Perhaps the silence is explained by factors we have not yet considered. Perhaps intelligent life tends to destroy itself. Perhaps civilizations choose not to communicate or communicate in ways we cannot detect. Perhaps the distances are simply too vast for any kind of contact. Or perhaps solar systems like ours, with all their peculiar features, are far rarer than we ever imagined. Tonight, let us drift deeper into the strangeness of what we have found among the stars. Let us examine some of the worlds that populate our catalogue of alien planets and understand why they seem so different from the familiar spheres of our own solar neighborhood. Begin with the hot Jupiters, those massive gas giants that orbit their stars in just a few days. When 51 Pegasi b was discovered in 1995, astronomers were puzzled. How could such a large planet exist so close to its star? The heat would be immense, the gravitational stresses extreme. Our models of planet formation had no place for such a body. The prevailing theory at the time held that gas giants must form far from their stars, beyond what is called the snow line, the distance at which water and other volatile compounds can exist as ice. Beyond the snow line, solid particles are abundant, allowing planetary cores to grow large enough to attract massive amounts of gas from the surrounding disk. Inside the snow line, the heat vaporizes these ices, leaving only rocky and metallic materials that can form terrestrial planets like Earth and Mars. Jupiter formed beyond our solar system's snow line, at roughly 3 to 5 astronomical units from the young sun. This allowed it to become the giant it is today, a world more than 300 times the mass of Earth, a failed star that never quite gathered enough material to ignite nuclear fusion in its core. But a hot, Jupiters orbit inside their snow lines, sometimes far inside. Some orbit closer to their stars than Mercury does to our Sun. How did they get there? The answer appears to be planetary migration. Planets do not necessarily stay where they form. Interactions with the gas and dust of the protoplanetary disk can cause them to drift inward or outward over millions of years. For hot Jupiters, it seems that many migrated inward from their birthplaces, spiraling toward their stars through the thick soup of the young disk. This migration can happen in several ways. The planet can lose angular momentum to the disk itself, gradually falling toward the star. Or gravitational interactions with other planets can fling a world onto a highly elliptical orbit that brings it close to the star, where tidal forces can circularize its path. Or a companion star in a binary system can perturb the planet's orbit over long timescales. gradually nudging it inward. What matters for our discussion is what happens to any small rocky planets that might be forming in the inner system when a gas giant comes ploughing through. The answer is usually nothing good. A migrating Jupiter would scatter smaller worlds, sending them careening into the star or ejecting them into the cold darkness of interstellar space. Hot Jupiter systems are likely to be lonely places, with the giant planet having swept the inner regions clean of any siblings. Our solar system has no hot Jupiter. Jupiter itself migrated, as we discussed, but it stopped and reversed course before it could reach the inner planets. This reversal preserved the space where Earth would eventually form. Had Jupiter kept falling inward, our planet would never have existed. Surveys suggest that hot Jupiters orbit around 1 to 2% of Sun-like stars. They are not overwhelmingly common, but they are common enough that their existence poses a challenge to habitability across the galaxy. Any star that hosts a hot Jupiter is unlikely to also host an Earth-like world in its habitable zone. But hot Jupiters are not the only strange category of planet we have discovered. Consider the super-Earths. A super-Earth is a planet more massive than our own, but less massive than Neptune. Typically, astronomers define super-Earths as worlds between 1 and 10 Earth masses, though the exact boundaries are debated. What is not debated is that super-Earths are extremely common. They appear to be one of the most frequently occurring types of planets in the galaxy, perhaps the most common type of all. And yet, as we have noted, our solar system has none. Earth is the largest rocky planet in our neighborhood. Beyond Earth, the next step up in mass is Uranus, which weighs in at nearly 15 Earth masses and is primarily composed of ices and gas rather than rock. There is nothing in between. No worlds of 2 or 3 or 5 Earth masses. Just a gap, an absence, a peculiar void in our planetary family. Scientists have proposed various explanations for this missing category. One leading hypothesis involves Jupiter and Saturn's early migration, the Grand Tack we discussed earlier. As Jupiter moved inward through the young solar system, it may have disrupted the formation of larger rocky planets, preventing super-Earths from coalescing. When Jupiter reversed course and moved outward again, the inner disk had already been depleted of much of its solid material. Only enough remained to build the modest terrestrial planets we see today: Mercury, Venus, Earth, and Mars. Computer simulations support this idea. When researchers model solar system formation without Jupiter's inward migration, super-Earths tend to form readily in the inner regions. When they include the Grand Tack, the super-Earths disappear, replaced by smaller worlds that more closely match what we actually observe. If this explanation is correct, it means the absence of super-Earths in our solar system is directly connected to the presence and behavior of Jupiter and Saturn. Our giant planets did not just protect us from impacts. They also sculpted the entire architecture of the inner solar system, determining what kinds of planets could form and where. This brings us to an uncomfortable question. Super-Earths are common elsewhere. Does that mean they are somehow incompatible with habitability? Or are we the strange ones? The answer is genuinely unclear. Super-Earths could potentially be habitable. A planet of 2 or 3 Earth masses would have stronger gravity, which could help it retain a thicker atmosphere. It might have more active plate tectonics, recycling carbon, and regulating climate over geological timescales. Some scientists have even argued that super-Earths might be more hospitable to life than Earth itself. But there are potential drawbacks. A more massive planet would have a thicker atmosphere, which could produce crushing surface pressures or a runaway greenhouse effect. The stronger gravity might make it difficult for life to develop complex body plans or for civilizations to develop spaceflight. And super-Earths that form close to their stars, as many appear to, would likely be tidally locked, with all the challenges that permanent hemispheric extremes would bring. The truth is that we do not yet know whether super-Earths are generally habitable or not. We have never visited one. We have never studied their atmospheres in detail. The James Webb Space Telescope is beginning to change this, peering at super-Earth atmospheres for the first time, but the data is still limited. What we can say is that our solar system took a different path. For whatever reason, whether by chance or by some deeper physical necessity, we ended up with no super-Earths, with a single, modest-sized rocky world in the habitable zone, with a specific configuration that allowed complex life to emerge over billions of years. Let us turn our attention now to another curious feature of our solar system, the diversity of our planets. When researchers from the University of Bern classified planetary system architectures, they found that most systems display what they called similar architecture. The planets in these systems tend to have comparable masses, like marbles in a row. If one planet is a certain size, its neighbors are likely to be close to that same size. The TRAPPIST-1 system is a good example. 7 Earth-sized planets orbiting a red dwarf star, all within a narrow range of masses and radii. The system looks almost like it was designed by an engineer who specified a certain planet template and then manufactured 7 copies. Our solar system is nothing like this. Mercury is tiny. Venus and Earth are roughly the same size. Mars is smaller again. Then you jump to the giants: Jupiter, Saturn, Uranus, Neptune. The mass ratios between neighboring planets vary wildly. Mercury is about 20 times less massive than Earth. Jupiter is over 300 times more massive than Earth. There is no peapod pattern here, no neat progression of similar worlds. This diversity may have implications for habitability. A system with many similar planets might have multiple worlds in or near the habitable zone, as TRAPPIST-1 does, but those worlds would also be gravitationally interacting with each other constantly, potentially destabilizing orbits over long timescales. In our solar system, Earth is the only planet in the habitable zone, but its orbit is protected by the great distances between itself and the giant planets. Perhaps the architecture of similar systems, while common, is not ideal for long-term stability. Perhaps the very diversity that makes our solar system unusual also makes it more stable over the billions of years needed for complex life to evolve. These are speculative ideas, but they highlight how little we still understand about the connection between planetary architecture and habitability. Each new discovery challenges our assumptions. Each strange world adds another data point to a picture that remains far from complete. Consider the mini-Neptunes, another common category of exoplanet, with no representative in our solar system. Mini-Neptunes are larger than super-Earths, but smaller than Neptune itself, typically 2 to 4 times Earth's radius. They appear to have thick atmospheres of hydrogen and helium wrapped around rocky or icy cores. Mini-Neptunes seem to be extraordinarily common around other stars. In many systems, they occupy the orbital positions where we might expect to find Earth-like worlds. They are particularly prevalent around red dwarf stars, which, as we mentioned, are the most common type of star in the galaxy. But our solar system has no mini-Neptunes. Neptune itself, at 17 Earth masses and nearly 4 times Earth's radius, is the smallest of our ice giants. There is nothing between Neptune-sized worlds and Earth-sized worlds in our planetary family. Another gap, another absence. Some researchers have suggested that mini-Neptunes represent a kind of default outcome for planet formation. Given enough raw material and enough time, perhaps most planetary systems naturally produce these puffy, gas-wrapped worlds. Our solar system, with its Jupiter-induced disruptions and its specific disk conditions, may have been prevented from following this standard path. If mini-Neptunes turn out to be poor candidates for life due to their thick atmospheres and likely lack of solid surfaces, then their prevalence across the galaxy could be another factor reducing the overall number of habitable worlds. The universe may be filled with planets that are common but inhospitable, while the rare planets like Earth remain hidden in the statistical noise. Let us pause here and consider the broader picture. When we began searching for exoplanets 3 decades ago, many astronomers expected to find solar systems like our own. Small rocky planets close in, giant planets far out, everything arranged in orderly circular orbits. The discovery of 51 Pegasi b was the first crack in this expectation. Every subsequent year has widened that crack into a chasm. We now know that hot Jupiters exist, super-Earths are common, mini-Neptunes are common, eccentric orbits are common. Planetary systems with all their planets clustered close to their star are common. Systems that look nothing like ours vastly outnumber systems that do. Among the more than 6,000 confirmed exoplanets, we have yet to find a true twin of our solar system. Not a single example of a system with small rocky planets in the inner regions, gas giants in the outer regions, circular orbits throughout, and an Earth-sized world in the habitable zone. Not one. This does not mean such systems do not exist. Our detection methods have biases. It is easier to find planets that are large, that orbit close to their stars, that transit across the stellar disk from our perspective. Small rocky planets in wide orbits are hard to detect. A true Earth analog around a Sun-like star would push the limits of our current technology. The James Webb Space Telescope is improving our ability to characterize the atmospheres of smaller planets. Future missions like the Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will help us find planets in wider orbits through gravitational microlensing. The European Space Agency's Plato mission will search for Earth-sized planets in Earth-like orbits around Sun-like stars. Within the next decade, we may finally begin to answer the question of how common or rare true solar system analogues really are. We may find that they are hiding in the data, waiting to be discovered. Or we may find that they are genuinely scarce, that our cosmic home is indeed an outlier in the vast population of planetary systems. For now, the evidence leans toward rarity. The patterns we see in the data, the architectures that dominate, the planet types that recur again and again, all suggest that our solar system took an unusual path through the space of possible configurations. And this brings us to a concept that scientists call the anthropic shadow. The anthropic principle, in its simplest form, states that we can only observe a universe capable of producing observers. We could not exist in a universe where the physical constants forbade the formation of stars, or where carbon could not be synthesized in stellar cores, or where galaxies never formed. The very fact that we are here to ask questions about the cosmos constrains the type of cosmos we can observe ourselves inhabiting. Applied to planetary systems, the anthropic principle suggests that we should not be surprised to find ourselves in a solar system capable of producing complex life, even if such systems are rare. If only 1 in a million planetary systems has the right combination of features, we would necessarily find ourselves in that 1 in a million system. The other 999,999 systems, inhospitable to intelligent observers, would have no one to notice their existence. This is the anthropic shadow, the selection effect that hides the true frequency of habitable planetary systems. We cannot observe the sterile worlds, the failed configurations, the solar systems, where no one ever evolved to build telescopes and ask questions. We can only observe ourselves here, in this place that apparently worked. Does this mean our solar system's apparent rarity is merely an illusion? That we are drawing conclusions from a biased sample of one? Not necessarily. The anthropic principle tells us why we find ourselves where we are, but it does not tell us how common such places are in absolute terms. We can still attempt to estimate the frequency of solar system analogues by studying the broader population of planetary systems. We can still ask whether the features that make Earth habitable are common or rare in the galaxy. What the anthropic principle does is remind us to be humble about our conclusions. We are not outside observers looking in at the distribution of planetary systems with perfect objectivity. We are participants embedded in one particular system, trying to understand the whole from our extremely limited vantage point. The universe may be teeming with planets, but the subset of those planets that can produce beings capable of contemplating the question may be vanishingly small, or it may not. We do not yet have enough data to say with confidence. What we do have is a growing catalogue of strange and wonderful worlds, planets that rain diamonds, planets with eternal sunsets on a terminator line between day and night, planets made of dense iron, planets inflated like balloons, planets shredded by their star's gravity into long tails of escaping gas. Each of these discoveries teaches us something about the processes that shape worlds. Each new data point refines our models of planet formation and evolution. And each apparent oddity, when enough similar cases accumulate, transforms from an outlier into a pattern, a new category of world we had never imagined. This is the beauty of exoplanet science. The universe has proven to be far more creative than we ever anticipated. The menagerie of planets we have found in just 3 decades exceeds any science fiction writer's imagination. We have been surprised again and again, and there is every reason to believe the surprises will continue. But amid all this diversity, our own solar system stands as something of an enigma. Not because it is normal and everything else is strange, but because it may be strange in its normalcy, unusual in its apparent orderliness, rare in the very features we once assumed were typical. The 8 worlds that circle our sun may be among the most precious configurations in the galaxy, not because they are intrinsically more important than any other planets, but because they happen to be ours, and because they happen to have produced us. This is not arrogance. It is simply the acknowledgement that whatever the true frequency of solar system analogues turns out to be, the combination of factors that produced Earth and allowed life to flourish here is non-trivial. It required specific conditions. It required certain events to happen and others to be avoided. It required 4 billion years of geological and biological evolution on a world that remained continuously habitable throughout that entire span. Many planets exist, but how many have remained habitable for 4 billion years? How many have avoided catastrophic asteroid impacts that sterilize the surface? How many have maintained stable climates, liquid water oceans, a protective magnetic field, an atmosphere that neither boiled away nor froze into global ice sheets? These questions do not have easy answers. The search for answers is one of the great scientific projects of our time. Let us continue our journey into the darkness and examine more closely some of the factors that may make our cosmic home so precious. The Milky Way stretches across the night sky like a river of light, a band of billions upon billions of stars so dense that individual points blend into a continuous glow. From our perspective on Earth, we see this river edge on, looking through the disk of our galaxy from our position within it. For most of human history, we did not understand what we were seeing. Ancient peoples imagined the Milky Way as spilled milk from the gods, or a road for souls traveling to the afterlife, or the spine of some great celestial creature. It was not until the early 20th century that astronomers confirmed what the Milky Way truly was. Our home galaxy, a vast spiral of some 200 to 400 billion stars rotating around a common center. Our Sun is one of those hundreds of billions of stars, and our position within the galaxy may be another factor contributing to the habitability of our solar system. The Milky Way is not uniform. Its density varies from region to region. Near the galactic center, stars are packed tightly together, sometimes separated by only a fraction of a light year. In the outer halo, stars are sparse, scattered lonely beacons in a vast emptiness. And within the spiral arms, where new stars are being born from collapsing clouds of gas and dust, conditions are turbulent and violent. Our solar system orbits the galactic center at a distance of approximately 27,000 light-years, placing us in a region of intermediate density. We are not in the thick of the galactic bulge, where gravitational interactions between passing stars could disrupt planetary orbits, and where radiation from the supermassive black hole at the center poses a significant threat. Nor are we in the sparse outer reaches, where the heavy elements needed to build rocky planets and living organisms are scarce. This intermediate zone is what scientists call the Galactic Habitable Zone, a ring-shaped region where conditions are thought to be most favorable for the development of complex life. The concept was formally proposed by researchers in the early 2000s, though the underlying ideas had been developing for decades. Several factors define the boundaries of the Galactic Habitable Zone. First is metallicity, the astronomical term for the abundance of elements heavier than hydrogen and helium. In astronomy, everything except hydrogen and helium is called a metal, a linguistic quirk that reflects the field's focus on fusion processes rather than chemical properties. Carbon, oxygen, silicon, iron, all of these are metals in the astronomical sense. Metals are essential for building rocky planets and for the chemistry of life. They are produced in the nuclear furnaces of massive stars and scattered across the galaxy when those stars explode as supernovae. Over billions of years, successive generations of stars have enriched the interstellar medium with heavier elements, but this enrichment is not uniform. Near the galactic center, where star formation has been occurring for the longest time and at the highest rates, metallicity is highest. Stars in this region are often rich in the elements needed to form planets. But they also face the dangers we mentioned: crowded stellar neighborhoods, intense radiation, gravitational disruptions. In the outer regions of the galaxy, metallicity drops off. Stars there formed from relatively pristine gas, with lower concentrations of the heavy elements needed to build Earth-like worlds. A planet forming around a low metallicity star might lack sufficient iron for a magnetic dynamo, sufficient silicon for a rocky crust, sufficient carbon for organic chemistry. The Galactic Habitable Zone represents a balance between these competing factors, far enough from the center to avoid the worst of the radiation and gravitational chaos, close enough to ensure sufficient metallicity for planet building. Our Sun appears to sit comfortably within this zone. Its metallicity is slightly higher than the galactic average, suggesting it formed from material that had been enriched by previous generations of stellar explosions. This chemical heritage may have been crucial for the formation of the rocky planets in our inner solar system, including Earth with its iron, core and silicate mantle. But position alone does not tell the whole story. Our orbit around the galactic center also matters. Spiral galaxies like the Milky Way are not static. The spiral arms rotate, though not as solid objects. They are density waves, regions where stars and gas temporarily bunch together before moving on. A star can pass through multiple spiral arm crossings over its lifetime, and each crossing brings potential hazards. Within the spiral arms, star formation is intense. Massive young stars burn hot and bright, and they die quickly, exploding as supernovae within just a few million years of their birth. A planet too close to a supernova could have its atmosphere stripped away by the blast of radiation, its ozone layer destroyed, its surface sterilized by cosmic rays. Our Sun orbits the galactic center at roughly the same angular velocity that the spiral arms rotate. This corrotation means that we pass through the spiral arms relatively rarely, perhaps once every 100 million to 200 million years. Between crossings, we drift through the quieter inter-arm regions, protected from the worst stellar violence. This is not a guarantee of safety. Supernovae can occur anywhere, not just in spiral arms. Passing stars can disrupt the Oort cloud, sending comets streaming into the inner solar system. And over the age of the solar system, we have undoubtedly experienced close encounters with dangerous events. But the statistical argument suggests that our galactic orbit has been relatively benign. We have avoided the most dangerous regions for long periods. We have not wandered into the dense stellar clusters near the galactic center. We have not been flung out into the metal-poor hinterlands. We have stayed in the quiet suburbs, far from the worst of the cosmic chaos. How common is such a fortunate orbit? That depends on how you define fortunate. Many stars share similar orbits to our Sun, drifting through the galactic disk at comparable distances from the center. But as we have seen, having the right galactic orbit is just one factor among many. A star with a perfect galactic orbit, but a system full of hot Jupiters, would still be unlikely to host habitable planets. The factors compound. Each favorable condition is perhaps not rare in isolation, but the intersection of all favorable conditions simultaneously may be quite rare indeed. A star in the galactic habitable zone, with the right metallicity, the right orbital stability, hosting planets with the right architecture, with no hot Jupiters, no super-Earths disrupting the habitable region, with giant planets in stable circular orbits that provide protection without destruction. This is the picture that emerges from our growing understanding of exoplanets and galactic dynamics. Not a universe hostile to life, but not necessarily a universe teeming with it either. A universe where the raw materials for life are common, but the specific configurations needed for its emergence and persistence may be considerably less so. Let us return now to the scale of individual solar systems and examine another factor that may contribute to our home's apparent rarity: the stability of planetary orbits. When we look at our 8 planets, one of their most striking features is how circular their orbits are. We measure orbital shape using a parameter called eccentricity, which ranges from 0 for a perfect circle to 1 for a parabola, an orbit so stretched that the object would escape the solar system entirely. Earth's orbital eccentricity is approximately 0.017. This means that while Earth's orbit is technically an ellipse, it is so close to circular that the difference between its closest approach to the Sun and its farthest distance is only about 5 million kilometers, roughly 3% of its average distance. Venus has an even more circular orbit, with an eccentricity of just 0.007. Neptune's eccentricity is 0.009. Jupiter comes in at 0.049, the highest among the 8 major planets, but still remarkably circular by the standards of what we observe elsewhere. When we look at exoplanets, the picture is dramatically different. The average eccentricity for exoplanets with orbital periods greater than 5 days is around 0.23. Many exoplanets have eccentricities of 0.5 or higher, meaning their orbits are highly elongated ellipses that bring them close to their stars at perihelion and sweep them far out into the cold at aphelion. A planet on a highly eccentric orbit experiences wild swings in temperature over the course of its year. At closest approach, it might be scorched by intense stellar radiation. At farthest distance, it might freeze. The atmosphere could partially escape during the hot phase. The surface could be alternately baked and frozen, and any climate stability would be impossible. For life as we know it, stable temperatures are important. Liquid water needs to persist on a planetary surface for billions of years to allow the slow process of biological evolution to unfold. A planet with wild orbital eccentricity would have a much harder time maintaining stable liquid water, even if it were the right distance from its star on average. Why do the planets in our solar system have such circular orbits while many exoplanets do not? Part of the answer relates to the number of planets in a system. Research has shown a strong correlation between planetary multiplicity and orbital eccentricity. Systems with more planets tend to have lower eccentricities. Systems with fewer planets show higher eccentricities on average. This makes sense dynamically. In a system with many planets, gravitational interactions between them tend to circularize orbits over time. If one planet's orbit becomes too eccentric, it will eventually have a close encounter with a neighbor, and the energy exchange will tend to reduce the eccentricity. The presence of multiple bodies creates a kind of orbital friction that damps down extreme orbital shapes. In systems with fewer planets, particularly systems that have experienced violent dynamical histories involving planet-planet scattering, eccentric orbits are more likely to persist. A planet that has been kicked by a close encounter with a giant world may retain its stretched orbit indefinitely if there are no other bodies to interact with. Our solar system has 8 major planets, enough to provide significant mutual gravitational influence. Over the 4.5 billion years since the planets formed, their orbits have been shaped and circularized by their interactions with each other. The result is the remarkably orderly arrangement we see today. But this raises another question. Why does our solar system have 8 planets in the first place? Why not 3 or 15, or just one giant world like so, many hot Jupiter systems? The answer likely comes back to the conditions present in the young solar nebula, the disk of gas and dust from which the planets formed. The mass of the disk, its composition, its temperature profile, its lifetime. All of these factors influenced what kinds of planets could form and how many. Our solar system appears to have formed from a disk that was neither too massive nor too sparse. Massive enough to form 4 terrestrial planets and 4 giant planets, but not so massive as to produce a swarm of super-Earths or trigger runaway migration of the giant planets into the inner system. And as we have discussed, the early migration history of Jupiter and Saturn played a crucial role. The Grand Tack scenario suggests that Jupiter moved inward and then outward again, sculpting the disk and determining what could form where. Without this specific history, our solar system might look very different. Different initial conditions, different planetary migration history, different number of planets, different orbital eccentricities. Each variation could have produced a solar system that was less favorable for habitability. The path our system took was not the only possible path, and it may not have been the most likely path. It was simply the path that happened to occur here, around this particular star, 4.5 billion years ago. Let us now consider the star at the center of our system. The Sun is a G-type main sequence star, a middle-aged yellow dwarf burning hydrogen in its core at a stable rate. It has been doing so for about 4.5 billion years and will continue for another 5 billion or so, before exhausting its hydrogen fuel and expanding into a red giant. This stability is important. The Sun's energy output has increased by about 30% over its lifetime, a gradual brightening that has been offset by changes in Earth's atmosphere and greenhouse gas concentrations. But the rate of change has been slow enough for life to adapt. There have been no sudden fluctuations that would have made the planet uninhabitable. The Sun's luminosity varies by only about 0.1% over its 11-year activity cycle. This is remarkably steady compared to many other stars. Some stars, particularly younger ones and red dwarfs, experience dramatic flares that can increase their brightness by factors of hundreds or even thousands for short periods. Such flares would bombard any nearby planets with intense ultraviolet and X-ray radiation, stripping away atmospheres and sterilizing surfaces. The Sun does flare occasionally. Solar storms can damage satellites and disrupt power grids on Earth. But compared to more active stars, our Sun is a relatively calm neighbor. It provides the energy life needs without regularly bathing our planet in lethal radiation. Red dwarf stars, which make up about 3/4 of all stars in the galaxy, present a different picture. They are small, cool, and long-lived. Some red dwarfs will continue burning for trillions of years, far longer than the current age of the universe. This longevity might seem favorable for life, providing enormous timescales for evolution. But red dwarfs are also prone to violent flaring, especially in their youth. A planet in the habitable zone of a red dwarf would orbit so close to its star that it would likely be tidally locked, with one face perpetually roasting in the stellar light, and the other frozen in eternal darkness. The transition zone between day and night, the terminator, might be habitable, but the conditions would be very different from what we experience on Earth. The TRAPPIST-1 system demonstrates both the potential and the challenges of red dwarf habitability. 7 Earth-sized planets orbit close together, with at least 3 in or near the habitable zone. But TRAPPIST-1 is known to flare, and the close proximity of the planets to the star means they are bathed in ultraviolet radiation whenever the star erupts. Whether any of these worlds have been able to retain atmospheres is still uncertain. Our Sun is not a red dwarf. It is a G-type star, larger and brighter and more stable. G-type stars make up only about 7% of all stars in the Milky Way. We orbit a relatively rare type of stellar furnace. Does this matter for habitability? Possibly. G-type stars offer a habitable zone that is farther from the star than for red dwarfs, reducing the likelihood of tidal locking. Their stability reduces the threat of atmospheric stripping by flares. and their moderate lifetimes around 10 billion years may provide the right timescale for complex life to evolve. Of course, we cannot conclude that only G-type stars can host habitable planets. Life might find a way around the challenges posed by red dwarfs, or K-type stars, which are intermediate between G-types and red dwarfs, might offer an even better combination of stability and longevity. We simply do not know yet. What we can say is that our Sun possesses a particular set of characteristics that have proven favorable for life on at least one planet. Stability, moderate luminosity, a lifespan long enough for billions of years of biological evolution. These are not guaranteed features. They are particular to our star, and they have contributed to making Earth what it is. The accumulation of special features continues. We have talked about our galactic position, our solar system architecture, our orbital stability, our stellar characteristics. Let us add one more factor to the list, our moon. The moon is unusual. Not just any moon, but specifically our moon, Luna, the grey sphere that lights our nights and drives our tides. Most moons in our solar system are either captured asteroids, small irregular bodies trapped by planetary gravity, or icy satellites formed in the outer solar system where water existed as ice. The inner planets have few moons. Mercury and Venus have none. Mars has 2 tiny captured asteroids, and then there is Earth, with a moon that is enormous relative to its parent planet. The moon is about 1/4 the diameter of Earth and about 1/80th of its mass. This is a staggering ratio. No other planet-moon pair in our solar system comes close. The moon is so large that the Earth-Moon system is sometimes called a double planet, rather than a planet with a moon. How did we end up with such an oversized companion? The leading theory is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized body, sometimes called Theia, struck the young Earth in a glancing blow. The collision was catastrophic. Much of both bodies was vaporized or melted. A vast cloud of debris was thrown into orbit around the shattered Earth, and from this cloud of molten rock, the moon coalesced. If this hypothesis is correct, the moon's existence is the result of a specific, violent event early in the solar system's history. Had Theia missed Earth, or struck it at a different angle, or been a different size, the outcome would have been different. We might have no moon at all, or a smaller moon, or multiple small moons. What does the moon do for Earth's habitability? First, it stabilizes our axial tilt. Earth rotates on an axis tilted at about 23 degrees relative to its orbital plane. This tilt gives us seasons, as different parts of the planet are tilted toward or away from the sun over the course of a year. But without the moon's gravitational influence, this tilt would be unstable. It would wobble chaotically, varying from nearly 0 degrees to perhaps 60 degrees or more over millions of years. Such wild variations in axial tilt would produce extreme climate swings. At 0 degrees tilt, there would be no seasons, and the tropics would bake while the poles froze permanently. At 60 degrees tilt, the seasons would be extreme, with each hemisphere experiencing months of perpetual sunlight, followed by months of perpetual darkness. Mars, with its tiny moons, exhibits exactly this kind of axial instability. Its tilt has varied dramatically over its history, contributing to the chaotic climate variations recorded in its polar ice caps. The moon anchors Earth's tilt, keeping it within a narrow range that has allowed climate to remain relatively stable for billions of years. This stability may have been crucial for the development of complex life. which seems to require long periods of relatively consistent conditions to evolve. Second, the moon drives ocean tides. The gravitational pull of the moon raises bulges in Earth's oceans, creating the regular cycle of high and low tides that coastal ecosystems depend upon. Some researchers have suggested that tidal pools, those intermediate environments between land and sea, may have been important sites for the origin of life, providing concentrated chemical environments where complex molecules could form and interact. Third, the moon gradually slows Earth's rotation through tidal friction. Early Earth rotated much faster than it does today, with days lasting only a few hours. Over billions of years, the moon's gravitational drag has slowed our rotation to its current 24-hour period. Slower rotation may have contributed to atmospheric circulation patterns favorable for life, though this connection is less certain than the axial tilt stabilization. Is a large moon essential for habitability? Not necessarily. Life might find ways to thrive on planets with unstable axial tilts or without significant tides. But the moon has certainly contributed to the specific conditions under which life has flourished on Earth. Its presence is another feature that makes our planetary system distinctive. And like so many other features we have discussed, a large moon formed by a giant impact is probably not common. Most planetary systems would not have experienced the precise geometry of impact that created Luna. Most planets would have no moon, or small captured moons, or moons formed in a completely different way. Our moon is a gift from a cosmic collision 4.5 billion years ago. It has shaped our planet's climate, our tides, our rotation, and perhaps our very existence as conscious beings. It is another strand in the tapestry of conditions that makes Earth what it is. How many more strands are there? How many additional factors, known and unknown, have contributed to making our planet habitable, while countless other worlds have remained sterile or hostile? We do not know the full answer. We may never know. But the picture emerging from our study of exoplanets is one of complexity and specificity. There does not appear to be a simple formula for habitability. There is instead a web of interconnected factors, each influencing the others, each capable of tipping a planet toward or away from the conditions life requires. Our solar system navigated this web successfully. Through some combination of chance and physical necessity, it produced at least one world where life could emerge and evolve for billions of years. Whether other systems have been equally successful is one of the great unanswered questions of our time. The year 2000 saw the publication of a book that would reshape how many scientists thought about life in the universe. It was called Rare Earth, and it was written by paleontologist Peter Ward and astronomer Donald Brownlee. Their argument was provocative. While simple microbial life might be common throughout the cosmos, complex life, the kind that eventually produces creatures capable of building telescopes and asking questions, is probably extraordinarily rare. Ward and Brownlee assembled an impressive list of factors they believed were necessary for complex life to evolve. A sun, like star in the galactic habitable zone, a rocky planet in the stellar habitable zone, a large moon to stabilize axial tilt, giant planets in the right orbits to provide protection without destruction, plate tectonics to recycle carbon and regulate climate, a magnetic field to shield the surface from cosmic radiation, enough water to form oceans, but not so much as to drown all the land. Each factor, they argued, was unlikely in isolation. And when you multiplied all the probabilities together, the chance of any given planet having all of them simultaneously became vanishingly small. Perhaps, they suggested, Earth was not just unusual, but unique. Perhaps we were alone in the observable universe. The rare Earth hypothesis sparked intense debate that continues to this day. Critics pointed out that many of the factors Ward and Brownlee cited were based on assumptions that might not hold. Perhaps life does not require plate tectonics. Perhaps magnetic fields are not as essential as assumed. Perhaps the specific features of our solar system are not necessary for habitability, but merely happen to be present on the one planet where we evolved. The critics had a point. When we have a sample size of 1, it is very difficult to separate the necessary from the contingent. Earth has plate tectonics, and Earth has complex life. But does that mean plate tectonics is required for complex life? Or did it simply happen to be present while complex life evolved for other reasons? This is the fundamental challenge of astrobiology. We cannot run controlled experiments. We cannot create 1,000 Earths with slightly different parameters and watch which ones develop life. We have only the natural experiments the universe has provided, the thousands of exoplanets with their varied characteristics, most of which we cannot study in sufficient detail to determine their habitability. The rare Earth hypothesis remains controversial. Some researchers embrace it, pointing to the accumulating evidence that solar system-like configurations are indeed uncommon. Others reject it, arguing that life is more adaptable than we assume, and that habitable conditions might be achieved through many different pathways, not just the specific pathway Earth happened to follow. What is less controversial is that the specific combination of features present on Earth is unusual. Whether those features are strictly necessary for complex life or merely sufficient is a question we cannot yet answer. But the fact that we have not found another solar system that looks quite like ours is a data point that must be explained. Let us examine some of the features Ward and Brownlee highlighted, beginning with plate tectonics. Earth's surface is divided into large plates of crust that move slowly over geological time, driven by convection currents in the underlying mantle. Where plates collide, mountains rise and volcanoes erupt. Where plates separate, new crust forms from upwelling magma. Where plates slide past each other, earthquakes shake the ground. This constant motion has profound effects on Earth's environment. It recycles carbon dioxide through the rock cycle, drawing the gas from the atmosphere into carbonate rocks at sea floors, and then returning it through volcanic outgassing. This cycle acts as a planetary thermostat, regulating Earth's temperature over millions of years. When carbon dioxide levels rise, the greenhouse effect warms the planet, increasing rainfall and accelerating the weathering of rocks. Weathering draws carbon dioxide from the atmosphere and carries it to the oceans, where it is incorporated into sediments and eventually subducted beneath the crust. The reduced carbon dioxide levels cool the planet. When carbon dioxide levels fall too low, the weakening greenhouse effect cools the planet, reducing rainfall and weathering. Volcanic outgassing continues to release carbon dioxide, but less of it is being removed. The gas accumulates, warming the planet again. This negative feedback loop has helped keep Earth's surface temperature within a habitable range for billions of years, even as the sun has gradually brightened. Without plate tectonics, this regulatory mechanism would not exist. Carbon dioxide would either accumulate to runaway greenhouse levels, as has happened on Venus, or be permanently sequestered in rocks, leaving the planet frozen. Venus and Mars, our nearest planetary neighbors, lack active plate tectonics. Venus is a hellscape, with surface temperatures hot enough to melt lead and an atmosphere 90 times denser than Earth's, composed almost entirely of carbon dioxide. Mars is frozen, its thin atmosphere providing little greenhouse warming, its volcanoes long dormant. Earth's plate tectonics may have saved us from either fate. By continually recycling carbon and regulating greenhouse gas levels, the moving plates have maintained the narrow temperature range in which liquid water can exist. But is plate tectonics common on rocky planets? We do not know. The conditions that enable plate tectonics are not fully understood. Earth may have the right combination of interior heat, mantle composition, and surface water to drive plate motion. Other planets may lack one or more of these requirements. Some researchers have suggested that super-Earths, those common planets 2 to 10 times more massive than our world, might have thick, stagnant crusts that prevent plate motion. The higher gravity and pressure could create a lithosphere too strong to break and subduct. If this is true, then the absence of super-Earths in our solar system might be connected to the presence of plate tectonics on Earth. This is speculative, but it illustrates how the various factors of habitability might be interconnected. Not having super-Earths may have allowed Earth to remain small enough for plate tectonics to operate. Plate tectonics may have regulated our climate over billions of years. The regulated climate may have allowed complex life to evolve. Each factor influences the others in ways we are only beginning to understand. Another factor Ward and Brownlee emphasized was Earth's magnetic field, generated by the churning motion of liquid iron in the planet's outer core. The magnetic field extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere. This magnetosphere deflects the solar wind, a stream of charged particles constantly flowing outward from the sun. Without the magnetic field, these particles would gradually strip away our atmosphere, atom by atom. Mars, which lost its global magnetic field billions of years ago, has experienced exactly this fate. Its once thicker atmosphere has been eroded by the solar wind, leaving behind the thin whisper of gas that exists today. The magnetic field also provides some protection against cosmic rays, high-energy particles from distant supernova, and other violent cosmic events. Cosmic rays can damage DNA and other biological molecules, posing a hazard to surface life. Is a magnetic field essential for habitability? The debate continues. Some researchers have argued that the magnetic field is crucial, that without it, Earth would have lost its atmosphere and become a frozen desert like Mars. Others have pointed out that Venus, despite lacking a significant magnetic field, has a very thick atmosphere. The relationship between magnetic fields and atmospheric retention may be more complex than simple models suggest. What is clear is that Earth does have a strong magnetic field, generated by specific conditions in its core. Not all planets have such fields. Mercury has a weak field. Venus has essentially none. Mars has only remnant magnetism in ancient rocks. Among the rocky planets of our solar system, Earth's magnetic field is uniquely strong and persistent. Whether this is necessary for complex life or merely a feature that happens to be present on the one planet where complex life exists, we cannot say with certainty. But it is another data point, another factor that distinguishes Earth from its neighbors. Let us turn now to water. Water is essential for all life as we know it. It is the solvent in which biochemistry occurs, the medium that carries nutrients and waste products, the molecule that participates in countless metabolic reactions. Without liquid water, life as we understand it could not exist. Earth has abundant water. It covers about 71% of our planet's surface, forming vast oceans that moderate our climate and host a rich diversity of life. But Earth is not a water world. 29% of our surface is land, rising above the sea in continents and islands. This balance may be important. Too little water, and there would be no oceans to support marine life, no water cycle to distribute rainfall over land, no moderating influence on climate. Too much water, and there would be no land at all. The planet would be covered in a global ocean, possibly hundreds of kilometers deep. What would such a water world mean for life? Simple life might do just fine. Microorganisms could thrive in a deep ocean, drawing energy from hydrothermal vents or other chemical sources. But complex life might struggle. Without land, there could be no forests, no grasslands, no land-based ecosystems. Without exposed rock, weathering would not draw carbon dioxide from the atmosphere, potentially destabilizing the climate. Without shallow coastal waters, the rich transitional environments where much of marine evolution has occurred might not exist. Some researchers have suggested that water worlds might be surprisingly common among rocky exoplanets. Planets that form beyond the snow, line and migrate inward would carry large amounts of ice with them. That ice would melt into vast oceans as the planet moved closer to its star. The result could be planets with far more water than Earth, perhaps 10 or 100 times as much. Earth appears to have just the right amount of water, enough to form extensive oceans, but not so much as to drown all the continents. How did we achieve this Goldilocks balance? The answer is not entirely clear. Some of Earth's water may have been delivered by comets and asteroids during the late heavy bombardment, a period of intense impacts about 4 billion years ago. Some may have been outgassed from the interior during volcanic eruptions. The exact sources and proportions remain debated. What seems likely is that the amount of water Earth received was influenced by the architecture of the solar system. Jupiter's gravitational influence determines which comets and asteroids can reach the inner solar system and which are deflected into deep space. The Grand Tack migration may have affected the distribution of icy bodies in the young solar system. The specific history of our planetary neighborhood determined how much water would eventually accumulate on Earth's surface. If this is true, then Earth's water content is not just a random variable. It is connected to the broader configuration of the solar system, to the positions and migrations of the giant planets, to the same factors we have been discussing throughout this exploration. Everything is connected. The giant planets influenced what kinds of inner planets could form. The inner planet sizes determined whether they could maintain plate tectonics and magnetic fields. The delivery of water depended on the dynamics of the outer solar system. The stability of the climate depended on the presence of a large moon. And through it all, the position of the Sun within the galaxy determined whether sufficient heavy elements were available to build any of this in the first place. This web of interconnections makes habitability seem like a delicate achievement, a precise balance that could be disrupted by any number of small changes. Change any one factor, and the whole system might tip into a different state, a different outcome, a lifeless world instead of one covered in forests and cities. But we should be cautious about this conclusion. The web of factors we see on Earth might not be the only possible web. Life might be achievable through different pathways that we have not imagined. There might be habitable planets without plate tectonics, without large moons, without magnetic fields, that have found other ways to maintain the conditions life requires. We are limited by our sample size of one. We have only Earth as a confirmed example of a planet with complex life. We cannot know which of Earth's features are essential and which are incidental without studying other examples. and those other examples, if they exist, may be scattered across the galaxy, separated from us by distances we cannot yet cross. The search for biosignatures, chemical signs of life in the atmospheres of distant exoplanets, is one of the great scientific challenges of our time. The James Webb Space Telescope is beginning this work, peering at the atmospheres of nearby super-Earths and mini-Neptunes, searching for combinations of gases that might indicate biological activity. Oxygen, in combination with methane, for example, would be difficult to explain without invoking life. These two gases react with each other and would not coexist in significant quantities for long unless something was continuously producing them. On Earth, that something is photosynthesis and methanogenesis, the metabolic activities of organisms. But detecting biosignatures is extraordinarily difficult. Exoplanet atmospheres are thin and distant. The light they filter or emit is a tiny fraction of the light from their parent stars. Teasing out atmospheric signatures requires enormous sensitivity and careful analysis. So far, we have not detected unambiguous biosignatures on any exoplanet. Some claims have been made and then disputed. The search continues. Perhaps within our lifetimes, we will have an answer. Perhaps we will find chemical evidence that life exists on another world, proving that Earth is not unique. Or perhaps we will search and find nothing, adding weight to the possibility that complex biospheres are rare indeed. Either outcome would be profound. Confirmation of alien life would transform our understanding of our place in the universe. Confirmation of solitude, that we are the only complex life in our cosmic neighborhood, would be equally transformative, placing upon us an awesome responsibility as the sole stewards of consciousness in this region of space. Let us consider what we might find if we could somehow travel to those distant worlds. Imagine arriving at a hot Jupiter system. The giant planet looms ahead, far larger than Jupiter, its cloud bands swirling with hypersonic winds. It orbits so close to its star that its year lasts only a few days. The star hangs enormous in the sky, a blazing disk that never sets, because the planet is tidally locked, its face permanently roasting. There are no small rocky worlds in this system. Whatever planets might once have formed in the inner regions were scattered or consumed when the hot Jupiter migrated inward. The habitable zone, the region where liquid water could exist, is occupied by nothing but the endless vacuum of space. Now imagine a system dominated by super-Earths. Several of these massive worlds orbit close to their star, their thick atmospheres shimmering with reflected light. Perhaps some have surfaces buried deep beneath thousands of kilometers of atmosphere, with pressures so intense that nothing familiar could survive. Perhaps others are water worlds, global oceans covering every inch of their surfaces, with abyssal depths that would crush any Earth submarine. Life might exist in such places. Microorganisms, floating in the upper atmospheres, drawing energy from starlight. Strange creatures in the dark depths of water-world oceans, forms of life utterly alien to anything on Earth. We cannot rule out these possibilities. But complex surface life, the kind that builds civilizations and asks questions about the cosmos, might be absent entirely. Now imagine arriving at a system that looks, from a distance, much like our own. A yellow star at the center, small rocky planets close in, giant planets far out, circular orbits, a quiet, orderly arrangement. You approach the third planet, the one in the habitable zone. It is the right size, about Earth mass. It has a thin atmosphere. You descend through the clouds. But the surface is wrong. Bare rock stretches to every horizon. No oceans, no plants, no life. Perhaps this world never received enough water during its formation. Perhaps it lost its water to a runaway greenhouse effect billions of years ago. Perhaps it has all the right architecture, but missed some crucial chemical ingredient, some trigger that would have started the cascade toward life. This might be the fate of most Earth-like planets, close, but not quite, almost habitable, but missing one key factor: the architecture of habitability without the spark of life. Or perhaps not. Perhaps some of those Earth-like worlds are teeming with life, are covered in alien forests, are home to beings who even now are building their own telescopes and pointing them at the sky, wondering if they are alone. We do not know. We cannot know, not yet. The distances are too vast, our instruments too limited, our understanding too incomplete. We can speculate and imagine and calculate probabilities, but we cannot confirm or deny the existence of alien life until we actually find it. What we can do is continue the search, continue building better telescopes, continue refining our models of planet formation and habitability, continue listening for signals from other civilizations, continue being curious about the universe and our place within it, and we can reflect on what we have learned about our own solar system, our own planet, our own extraordinary circumstances. We are rare, perhaps not unique, but rare. The evidence points toward a universe where habitable configurations are the exception rather than the rule, where most planets are too hot or too cold, too big or too small, too close to their stars or too far away, where most solar systems have the wrong architecture, the wrong stellar type, the wrong galactic location. This rarity is not cause for despair. It is cause for wonder. We have won a cosmic lottery, not through any merit of our own, but through the blind workings of physics and chemistry over billions of years. The atoms that make up our bodies were forged in the cores of ancient stars. The planets that surround us were sculpted by gravitational forces we are only beginning to understand. The very fact that we exist, that we can ask questions about our existence, is a testament to an improbable sequence of events stretching back to the birth of the universe itself. We are stardust that became aware of itself. We are the universe contemplating its own nature. We are, as far as we know, extraordinarily rare, and that makes us extraordinarily precious. 4.5 billion years. That is the age of our solar system, give or take a few million. It is a span of time so vast that the human mind struggles to comprehend it. If you represented the age of the solar system as a single year, all of recorded human history would fit into the last half second before midnight on December 31st. In that immense stretch of time, our solar system has maintained its fundamental architecture. The planets have continued to orbit the Sun in roughly the same configurations they achieved after the chaos of formation settled down. Earth has remained in the habitable zone, neither spiraling toward the Sun nor drifting outward into the cold. The giant planets have stayed in their distant orbits, providing gravitational stability without catastrophic disruption. This long-term stability is itself a remarkable feature. Planetary systems are chaotic in the mathematical sense. Small perturbations can accumulate over time, leading to dramatically different outcomes. Run the clock forward or backward by billions of years, and the precise positions and velocities of the planets become unpredictable. Yet despite this underlying chaos, our solar system has remained functionally stable, with no collisions between major planets, no ejections into interstellar space, no catastrophic reorganizations. Computer simulations of solar system dynamics suggest that this stability is not guaranteed. Some simulations show Mercury's orbit becoming unstable in the distant future, with a small but non-zero probability of a collision with Venus, or even an ejection from the solar system within the next few billion years. Other simulations show the system remaining stable for far longer than the sun will continue to shine. The uncertainty arises from the chaotic nature of gravitational dynamics. We cannot predict the exact state of the solar system billions of years from now, because we cannot know the initial conditions precisely enough. The tiniest uncertainty in the current positions and velocities of the planets grows exponentially over time, eventually making long-term predictions impossible. But what the simulations tell us is that our solar system exists within a region of stability, a configuration where the orbits are far enough apart and circular enough that catastrophic instabilities are unlikely on the timescales relevant to life. We occupy an island of calm in a vast ocean of possible chaotic configurations. Many other planetary systems likely do not enjoy this stability. Systems with giant planets on eccentric orbits, or with planets packed closely together, or with resonances that slowly pump up orbital eccentricities, may be inherently unstable. Planets in such systems might collide or be ejected within millions or tens of millions of years. Complex life would have no chance to evolve. Our stability has given life billions of years to develop. From the first simple cells to the vast complexity of modern ecosystems, evolution has had the time it needed. Had our solar system been unstable, had Earth's orbit changed dramatically over geological time, the continuity of life might have been impossible. Consider what has happened on our planet over those billions of years. About 4 billion years ago, life appeared. We are not certain exactly how, but the evidence suggests it happened remarkably quickly after the planet cooled enough for liquid water to persist on its surface. Simple cells, probably similar to modern bacteria and archaea, emerged in the primordial oceans. For roughly the next 2 billion years, life remained simple. Single-celled organisms dominated the planet, slowly changing the composition of the atmosphere through their metabolic activities. Photosynthetic organisms evolved, releasing oxygen as a waste product. This oxygen gradually accumulated, eventually reaching levels that could support more complex forms of life. About 2 billion years ago, a revolutionary event occurred. One simple cell engulfed another, and instead of digesting it, the two formed a partnership. The engulfed cell became the mitochondrion, the powerhouse of the eukaryotic cell. This symbiosis created a new type of organism with far greater metabolic capabilities than any simple cell. The eukaryotes had arrived. For another billion years or so, life remained unicellular, though the cells were now more complex. Then, around 600 million years ago, multicellular life exploded onto the scene. The Cambrian explosion saw the rapid diversification of animal body plans. Suddenly, the oceans were filled with creatures of astonishing variety. Trilobites and worms, mollusks and arthropods, the ancestors of every animal phylum we see today. Plants colonized the land about 500 million years ago, followed by animals. Forests grew and fell. Continents drifted and collided. Mass extinctions wiped out vast percentages of species, only for life to recover and diversify anew. Dinosaurs ruled for over 150 million years before an asteroid impact ended their reign. Mammals rose to prominence. Primates evolved. And eventually, in the last few 100,000 years, a species emerged that could contemplate the stars and ask questions about its origins. All of this required time. Billions of years of continuous habitability. A planet that remained in the habitable zone, with liquid, water on its surface, with a stable climate that allowed life to persist even as it transformed itself. Had any of the factors we have discussed been different, had the solar system been unstable, had the sun been more variable, had Jupiter migrated all the way in, this long chronicle of life would have been cut short or never begun. The story of life on Earth is a story of contingency and persistence. Contingency because so many events could have gone differently. Persistence because against all odds, the conditions for life have been maintained for nearly as long as the solar system has existed. Can we expect the same story to have unfolded elsewhere? Perhaps. Somewhere in the vastness of the galaxy, there may be other worlds where life has had billions of years to evolve. Other places where the architecture of the planetary system and the stability of the star have conspired to create a continuous haven for living things. Other biospheres that have passed through their own versions of the Cambrian explosion, their own mass extinctions, their own emergences of intelligence. Or perhaps not. Perhaps the conditions that allowed Earth's long history of life are genuinely rare. Perhaps most planetary systems cannot maintain habitability for billions of years. Perhaps the combination of factors we have been discussing is so unusual that we are among the very few places in the galaxy where complex life has had a chance to evolve. The question remains open. The data we have collected so far leans toward rarity, but it does not conclusively prove it. The search continues. Let us now look forward to what the future might reveal. Within the next decade, new telescopes and missions will dramatically expand our understanding of exoplanets and their potential for life. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will use gravitational microlensing to detect planets that are too far from their stars and too faint to find by other methods. This technique will be particularly sensitive to planets in wide orbits, the cold Jupiters and cold Neptunes that might play important roles in planetary system architecture. Roman may help us determine how common solar system-like configurations really are. The European Space Agency's Plato mission will search for rocky planets in the habitable zones of Sun-like stars. Plato will study brighter stars than Kepler did, enabling more detailed follow-up observations of any promising candidates. If there are Earth twins out there, Plato has a good chance of finding them. On the ground, the extremely large telescope being built in Chile, with a primary mirror 39 meters across, will have the power to directly image some exoplanets and analyze their atmospheres in unprecedented detail. Combined with space-based observations from Webb and its successors, this capability may finally reveal whether any nearby exoplanets harbor signs of life. The search for biosignatures will intensify. Oxygen combined with methane, as we discussed, would be a strong indicator of biological activity. But there may be other signs. Unusual ratios of isotopes, gases that should not persist without continuous production, spectral features we have not yet learned to interpret. We might also detect technosignatures, evidence of technological civilizations. Radio telescopes continue to listen for signals from other stars. The search for extraterrestrial intelligence, SETI, has been ongoing for over 60 years without a confirmed detection. But the search has been limited, covering only a tiny fraction of the possible frequencies and directions and time periods. A signal might be waiting to be found, hidden in the noise, if only we look in the right place at the right time. Some researchers have proposed searching for evidence of megastructures, vast engineering projects that might be visible across interstellar distances. Others have suggested looking for industrial pollutants in exoplanet atmospheres, or laser communications between distant worlds, or the waste heat signatures of advanced civilizations. So far, all of these searches have come up empty. The silence of the cosmos continues. But absence of evidence is not evidence of absence, and the search has only begun. We may simply not have looked hard enough, or in the right ways, or at the right places. If we do detect signs of life elsewhere, whether microbial biosignatures on a super-Earth or radio signals from an advanced civilization, the implications would be staggering. We would know that life is not unique to Earth, that the processes that produced us have operated elsewhere, that we are part of a cosmic community of living things. If we continue to search and find nothing, the implications would be equally significant. We would be forced to confront the possibility that we are truly alone, or at least extraordinarily isolated, in a universe vast beyond comprehension. The responsibility of being the sole bearers of consciousness in this region of space would rest upon our shoulders. Either way, the search is worth conducting. Either answer would transform our understanding of ourselves and our place in the cosmos. We cannot not look. We are creatures driven by curiosity, by the need to know, by the desire to find our kindred among the stars. Let us return for a moment to our own solar system and appreciate what we have. 8 worlds circling a stable star, 4 rocky planets in the inner system, including 1 with blue oceans and green continents, teeming with life, 4 giant planets in the outer system, ice giants and gas giants with their retinues of moons and rings, an asteroid belt rich in metals and minerals, a vast reservoir of comets in the frozen outer reaches, and at the center, a yellow star that has burned steadily for 4.5 billion years and will continue to burn for another 5 billion more. This is home. This is the only planetary system we have ever known directly, the only one we have explored with spacecraft and walked upon with human feet. It is familiar to us, perhaps too familiar. We take it for granted because we have never known anything else. But the lesson of exoplanet science is that we should not take it for granted. Our solar system is not typical. It is not a template for what planetary systems look like. It is one configuration among many, and apparently one of the rarer configurations at that. We live in an unusual place. Our sun is an unusual star. Our planets trace unusual orbits. Our very existence is an unusual outcome in a universe of possibilities. This does not mean we are special in some cosmic or spiritual sense. The universe does not care about us. The laws of physics do not favor life. We are here because atoms can combine into molecules. Molecules can combine into cells. Cells can combine into organisms. And organisms can combine into ecosystems, all without any intention or plan. But we can care about ourselves. We can recognize the preciousness of what we have. We can appreciate that the conditions for our existence are not guaranteed, are not common, are not easily replicated. And perhaps this recognition can inform how we treat our planet and each other. If Earth is rare, if solar systems like ours are uncommon, if complex life is precious, then we have a responsibility to preserve what we have. The damage we do to our biosphere, the extinctions we cause, the climate we destabilize, all of this takes on a different meaning when viewed through the lens of cosmic rarity. We may be destroying something irreplaceable. Not just irreplaceable to us, but potentially irreplaceable in the galaxy. If complex biospheres are rare, then every species we drive to extinction, every ecosystem we degrade, represents a loss not just to humanity, but to the cosmos itself. This is a heavy thought. It places a weight of responsibility upon us that earlier generations did not have to bear. They did not know what we know about the apparent rarity of our situation. They could imagine that the universe was filled with Earths, that whatever we destroyed here would exist in abundance elsewhere. We can no longer take that comfort. The evidence suggests that Earths may be few and far between. The conditions for complex life may be narrowly defined. We may be custodians of something precious beyond measure. Let us carry this thought with us as we continue our journey through the darkness, as we search for other worlds and wonder whether they might host life of their own. The universe is vast. The numbers are staggering. Hundreds of billions of stars in our galaxy alone. Hundreds of billions of galaxies in the observable universe. Planets beyond counting, worlds beyond imagining, configurations we have not yet dreamed of. And yet, among all of this, worlds like ours may be rare. The specific combination of factors that produced Earth, that allowed life to emerge and evolve, and eventually produce beings who could ask questions about their own existence, this combination may be uncommon in the extreme. We are children of a remarkable home, a planetary system that somehow threaded the needle of habitability, a planet that has remained welcoming to life for nearly 4 billion years. A lineage of organisms that has survived mass extinctions, ice ages, asteroid impacts, and the slow transformation of our star. We have much still to learn. The story of our solar system's rarity is not yet complete. New discoveries may revise our understanding, may reveal that solar system analogues are more common than we currently believe, or may confirm and deepen our sense of just how unusual our home really is. But for now, let us rest in the wonder of it all. Let us appreciate the darkness between the stars, the silence that surrounds us, the apparent absence of companions in this vast cosmic emptiness. Let us hold in our minds the image of 6,000 distant worlds, each one strange, each one unlike our own, each one a reminder that the universe does not easily produce what we take for granted. And let us feel, perhaps, a quiet gratitude for the improbable sequence of events that brought us here. The collapse of a molecular cloud, the ignition of a star, the migration of giants, the bombardment of comets, the rise of continents and the filling of oceans, the slow, patient work of evolution over eons, and finally, the emergence of creatures who could look up at the night sky and wonder. We are the universe looking back at itself. We are Stardust awakened. We are, as far as the evidence suggests, extraordinarily rare. And that makes this moment, this existence, this pale blue dot in the cosmic dark, something worth cherishing. As we drift toward the end of our journey tonight, let us gather together the threads we have woven and see what pattern emerges. We began with a question: how rare is our solar system? The answer, as we have seen, is not simple. It requires us to consider multiple factors, each contributing to the overall picture of our cosmic home's unusualness. First, there is the architecture of our planetary system. 8 planets orbiting in near circular paths, rocky worlds in the inner regions, gas giants in the outer reaches, a clear progression from small to large as you move away from the sun. This ordered architecture, as researchers have classified it, appears to be the rarest of the 4 main types of planetary system configurations. Most systems have similar-sized planets throughout, like peas in a pod. Our diversity is unusual. Second, there is the absence of certain planet types. No hot Jupiters scorching close to the sun. No super-Earths filling the mass gap between our rocky worlds and the ice giants. No mini-Neptunes in the inner system. These are among the most common planet types in the galaxy, and yet we have none of them. Our solar system is missing the most popular players. Third, there are the giant planets themselves. Jupiter and Saturn, in their specific positions and on their nearly circular orbits, have played a crucial role in shaping the inner solar system. The Grand Tack migration, if the hypothesis is correct, prevented the formation of super-Earths and preserved the space where Earth would eventually form. The presence of two gas giants in a gravitational resonance that caused them to move outward rather than inward is not something we should expect to find commonly. Fourth, there is our star. The Sun is a G-type main sequence star, larger and brighter than the red dwarfs that make up the majority of the galaxy's stellar population. It is remarkably stable, with low luminosity variation over its activity cycle. It provides consistent energy to its planets without the violent flares that plague many smaller stars. Only a few % of stars share these characteristics. Fifth, there is our position in the galaxy. We orbit in the galactic habitable zone, far enough from the dangerous center to avoid the worst radiation and gravitational disruptions, close enough to have received sufficient heavy elements for planet building. Our orbit around the galactic center is nearly synchronous with the rotation of the spiral arms, meaning we pass through those dangerous regions of star formation relatively rarely. We occupy a quiet corner of a vast and often violent galaxy. Sixth, there are the specific features of Earth itself. Plate tectonics recycling carbon and regulating climate. A magnetic field deflecting solar wind and cosmic rays. Enough water to form oceans, but not so much as to drown all the continents. A large moon stabilizing our axial tilt and providing long-term climatic stability. Each of these features may or may not be essential for complex life, but each distinguishes our planet from the majority of worlds we have observed. Seventh, and perhaps most importantly, there is time. Our solar system has maintained its favorable configuration for 4.5 billion years. Earth has remained habitable for nearly as long. This long-term stability has given life the opportunity to evolve from simple cells to complex ecosystems to intelligent beings capable of contemplating the cosmos. Systems that are unstable, that undergo catastrophic reorganizations or lose their habitable conditions after only a few 100 million years, would not provide this opportunity. When we consider all of these factors together, the picture that emerges is one of apparent rarity. Not every factor is necessarily essential for habitability. Life might find ways to flourish without plate tectonics, without a large moon, without the exact configuration of giant planets we possess. But the combination of factors present in our solar system is clearly unusual when compared to the population of exoplanets we have discovered. This does not mean we are unique. The galaxy is vast, and even rare configurations will occur many times when the sample size is hundreds of billions of stars. If solar system analogues occur around only 1 in a million stars, there would still be hundreds of thousands of them in the Milky Way alone. If the rate is 1 in a billion, there would still be hundreds, but the distances between such systems would be immense. Hundreds or thousands of light years might separate one potentially habitable solar system from the next. Communication would take centuries or millennia. Travel, with any technology we can currently imagine, would take far longer. Each habitable island in the cosmic ocean might be effectively alone, surrounded by vast stretches of empty space and sterile worlds. This isolation might explain the silence we observe. The Fermi paradox, The apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence has puzzled scientists for decades. Many solutions have been proposed. Perhaps civilizations tend to destroy themselves before they become spacefaring. Perhaps they choose not to communicate. Perhaps they are communicating in ways we cannot detect. But another solution is simply rarity. Perhaps technological civilizations are extraordinarily uncommon because the conditions for their emergence are extraordinarily uncommon. Perhaps the specific sequence of events required, a solar system with the right architecture, a planet with the right characteristics, billions of years of continuous habitability, the evolution of intelligence, the development of technology, is so unlikely that it has happened only a handful of times in our galaxy's history. If this is true, then the silence makes sense. There may be no one to talk to because there is almost no one out there. The galaxy may be filled with stars and planets, but nearly empty of minds. This is a sobering thought. It places our existence in a different light. We are not one civilization among many, easily replaced if we should disappear. We may be one of the very few, perhaps the only one in our cosmic neighborhood, perhaps the only one in the entire galaxy. The weight of this possibility is profound. It suggests that what happens on our small planet matters not just to us, but potentially to the cosmos itself. If intelligence is rare, if consciousness is precious, then our stewardship of Earth takes on cosmic significance. We are not just preserving our own heritage. We may be preserving something that exists nowhere else within millions of light years. Of course, we cannot be certain of any of this. The data is still incomplete. New discoveries could change the picture dramatically. Perhaps the James Webb Space Telescope will find biosignatures on a nearby super-Earth tomorrow. Perhaps radio astronomers will detect a signal from a distant civilization next week. Perhaps the universe is teeming with life and we have simply not looked in the right places yet. We must hold our conclusions lightly. Science is a process of continual revision, and the science of exoplanets is still young. What seems rare today might prove common tomorrow. What seems impossible might prove inevitable. But for now, let us rest in what we know. Let us appreciate the extraordinary journey that has brought us to this moment of understanding. Let us feel the weight of the cosmos pressing in around us, the vastness of the distances, the profusion of stars, the silence between them. And let us find in that silence not despair but wonder, not loneliness but peace. The universe does not owe us companions. It does not owe us meaning. It does not owe us anything at all. It simply is vast and ancient and utterly indifferent to our hopes and fears. And yet, within this indifferent cosmos, something remarkable has happened. Matter has organized itself into forms that can contemplate their own existence. Atoms have assembled into molecules, molecules into cells, cells into organisms, organisms into beings that look up at the stars and ask why. We are that asking. We are the universe's way of knowing itself. Whatever the answer to our questions, whatever the true prevalence of life in the cosmos, this much is certain. The fact that we exist to ask is extraordinary. The fact that we can wonder is wonderful. So let us wonder. Let us appreciate the darkness and the light. Let us hold in our minds the image of our solar system, that improbable arrangement of worlds, spinning through the galactic disk like a tiny island of order in an ocean of chaos. Mercury, closest to the sun, a small dense world baked and frozen by turns as it slowly rotates through its 2-year-long day. Venus, shrouded in clouds of sulfuric acid, its surface hotter than any oven, a cautionary tale of runaway greenhouse effects. Earth, Our home, blue and white and green, the only place we know for certain that life exists. Mars, red and cold and silent, bearing the scars of a more watery past, perhaps harboring microbial life in hidden subsurface oases. Beyond the asteroid belt, the giants reign. Jupiter, massive and turbulent, with its great red spot storm raging for centuries, its dozens of moons forming a miniature solar system of their own. Saturn, jeweled with rings of ice and rock, ethereally beautiful, less dense than water despite being nearly 100 times Earth's mass. Uranus and Neptune, the ice giants, cold and distant, their blue and blue-green atmospheres hiding mysteries we have only begun to explore. And beyond even these, the scattered disk and the Oort cloud, vast reservoirs of frozen debris left over from the solar system's formation, stretching outward for light years until they merge with the interstellar medium. This is our neighborhood. This is the system that has sheltered life for billions of years. This is what the universe happened to produce around one unremarkable yellow star in one unremarkable arm of one unremarkable galaxy. Except it may not be unremarkable at all. The evidence suggests it may be quite remarkable indeed. As you drift towards sleep tonight, carry this thought with you. You exist in an extraordinary place. Your atoms were forged in the hearts of ancient stars. Your planet has remained habitable for 4 billion years, through some combination of physics and luck and cosmic architecture that may be rare in the extreme. You are the inheritor of an unbroken chain of life stretching back to the first simple cells in the primordial ocean. All of this had to happen for you to be here, listening to these words, contemplating the stars. All of this improbability, all of this contingency, all of these narrow escapes and fortunate accidents have converged in this moment, in this place, in you. The universe is under no obligation to make sense. It is under no obligation to produce life or consciousness or wonder. And yet, it has. Against all apparent odds, here we are. Let the darkness between the stars hold no terror for you. Let the silence of the cosmos bring no sorrow. We do not need the universe to be filled with companions to find meaning in our existence. We do not need to be common to be valuable. Perhaps we are rare. Perhaps we are precious. Perhaps the very fact of our existence is something worth celebrating, regardless of whether anyone else in the galaxy is there to celebrate with us. The search will continue. New telescopes will peer deeper into the darkness. New missions will explore new worlds. New generations will ask the same questions we asked tonight, and perhaps they will find answers we cannot imagine. But for now, let us rest in the mystery. Let us appreciate what we have. Let us feel the rotation of our planet beneath us, carrying us through the darkness toward another dawn. Let us sense the pull of the sun, holding us in our orbit, warming our world, making life possible. We are small. We are brief. We are specks of consciousness flickering for a moment in the vast darkness of space and time. And yet we are here. Against all odds, against all probability, against the apparent rarity of configurations like our solar system, we are here. This is enough. This is more than enough. This is everything. The night sky wheels overhead, the same stars that our ancestors watched, the same stars that will shine long after we are gone. Among them, hidden in the light, are thousands of worlds we have discovered, and billions more we have not. Most of them are strange. Most of them are unlike our home. Most of them, perhaps, could never have produced beings like us. But here, on this small blue world, orbiting this modest yellow star, in this quiet corner of the galaxy, life has found a way. Consciousness has emerged. Questions are being asked. And in the asking, something beautiful is happening. The universe is becoming aware of itself. Matter is contemplating matter. Stardust is wondering about stars. This is the gift of our rare solar system. This is what the improbable architecture of our cosmic home has made possible. Not just life, but the awareness of life. Not just existence, but the contemplation of existence. Whatever else the universe may or may not contain, it contains this moment. It contains you, listening in the darkness. It contains the wonder you feel when you consider the vastness of space and the apparent rarity of places like Earth. Hold on to that wonder. Let it accompany you into sleep. Let it infuse your dreams with the light of distant suns and the silence of the cosmic void. You are part of something extraordinary. You are the product of an extraordinary place. And that place, our solar system, may be rarer and more precious than humanity ever imagined. The stars are calling, but they speak in riddles. The silence between them is profound, but it is not empty. It is filled with possibility, with questions waiting to be answered, with mysteries waiting to be solved. And we, rare as we may be, are here to listen. We are here to wonder. We are here to ask. This is our gift and our burden. This is what it means to be conscious in a cosmos that may not often produce consciousness. This is the responsibility and the privilege of being human on a planet that may be one of the few harbors of complex life in the galaxy. Let us be worthy of it. Let us cherish what we have. Let us continue the search for others like us, even as we appreciate the possibility that such others may be few and far between. The night deepens. The stars continue their ancient dance. And we, small and brief and improbable, drift toward dreams on a world that may be more extraordinary than we ever knew. Rest now. Let the vastness of space cradle you. Let the silence of the cosmos sing you to sleep. Tomorrow, the search continues. Tomorrow, new data will arrive from distant worlds. Tomorrow, we may learn something that changes everything we thought we knew. But tonight, let us simply be grateful. Grateful for the solar system that produced us. Grateful for the planet that sustains us. Grateful for the rare and precious gift of being alive, being aware, being here. Among all the worlds, in all the galaxies, in all the universe, this is where we find ourselves, this improbable place, this extraordinary home, our solar system, rare perhaps, precious certainly, and ours for as long as we have the wisdom to protect it. The stars fade as sleep approaches. The questions fade with them, dissolving into dreams. But the wonder remains. The wonder is always there, waiting for us when we wake, ready to guide us through another day of discovery. For we are explorers, we, humans. We are askers of questions. We are seekers of truth in a universe that guards its secrets closely. And whatever we find, whether companions among the stars or only the vast and beautiful silence, we will face it with courage. We will face it with curiosity. We will face it together, as the rarest of creatures on the rarest of worlds, looking out at the cosmos and daring to ask, what else is out there? The answer, when it comes, will be worth the wait. The search, while it continues, is worth the effort. And the journey, through space and time and the depths of our own wonder, is worth every moment. Sleep well, dream of stars, and know that you are part of something vast and ancient and wonderful, something that began with the birth of our solar system 4.5 billion years ago and will continue long after we are gone. We are stardust, dreaming of stars. We are the universe, wondering at itself. And that, perhaps, is the rarest and most precious thing of all. The darkness embraces us. The silence holds us. And in the quiet of the cosmic night, we rest, knowing that when we wake, the stars will still be there, the questions will still call to us, and the great adventure of understanding our place in the universe will continue. For we are curious, we are brave, we are the children of an extraordinary solar system, and we will not rest until we know whether others like us exist among the stars. But for now, sleep. For now, peace. For now, the gentle drift into dreams cradled by the same gravity that holds our planet in its orbit, warmed by the same star that has burned steadily for billions of years. We are home. We are safe. We are exactly where we are supposed to be, in the rarest of places, on the most precious of worlds, under the most extraordinary of circumstances. And that is enough. That is more than enough. That is everything. Good night. Before we close our eyes completely, let us take one more journey through the gallery of strange worlds that populate our growing catalogue of exoplanets. Each discovery tells a story. Each world reveals something about the processes that shape planets and determine their fates. Consider the rogue planets, those wanderers that drift through the galaxy without any star to call home. Just weeks ago, in early January 2026, astronomers announced the discovery of a Saturn-mass rogue planet some 10,000 light-years away. This was a breakthrough observation because, for the first time, scientists used both ground-based telescopes and space-based observatories simultaneously to make the detection. And for the first time, they were able to directly measure a rogue planet's mass, rather than merely estimating it. Rogue planets are born in planetary systems like any other world, but at some point in their history, gravitational interactions with sibling planets or passing stars fling them out of their birth systems entirely. They sail off into the darkness, cooling slowly over billions of years, carrying whatever internal heat they retain from their formation. How many rogue planets exist? The estimates are staggering. Some researchers believe there may be more rogue planets in the galaxy than planets orbiting stars. Billions, or even trillions of these dark wanderers could be drifting between the stars, invisible except when they happen to pass in front of a background star and reveal themselves through gravitational lensing. Our solar system has apparently avoided producing rogue planets, at least none that we know of. The orderly arrangement of our 8 worlds suggests that any major ejections would have occurred very early in the solar system's history, if at all. This stability is another factor that distinguishes our planetary system from others that may have experienced more violent dynamical histories. Think about what it would mean to live on a rogue planet if such a thing were possible. No sun in the sky, no seasons, no day and night cycle. Only the eternal darkness of interstellar space, punctuated perhaps by the faint points of distant stars. Any life on such a world would have to survive on internal heat alone, perhaps huddled around volcanic vents or deep beneath an icy surface where radioactive decay warms the rock. It is a haunting image, a world alone in the void, carrying whatever life or potential for life it might possess, drifting for billions of years without destination or purpose. And yet, even this strange existence is a form of cosmic creativity. The universe has found ways to make planets and set them loose among the stars. Whatever else happens, whatever life does or does not arise, the sheer diversity of outcomes is remarkable. Let us also consider the planets that orbit multiple stars. In our solar system, we have a single star at the center. But many planetary systems are not so simple. Binary star systems, where two stars orbit each other are common in the galaxy, and we have now discovered planets that orbit both stars in such systems, tracing complex paths around their twin suns. The fictional planet Tatooine in Star Wars, with its famous double sunset, turns out to have real-world counterparts. Astronomers have found circumbinary planets, as they are called, in several systems. Just recently, images were captured of one such planet with an unusual 300-year orbit around its binary hosts. Life on a circumbinary planet would experience strange patterns of day and night. Sometimes both suns would be in the sky together, flooding the surface with light. Sometimes they would be on opposite sides of the planet, creating a day without true darkness. The seasons would be complicated by the binary orbit, with varying distances to each star, producing overlapping cycles of warming and cooling. Could complex life evolve on such a world? We do not know. The changing light conditions might make photosynthesis difficult to optimize. The gravitational perturbations from two stars might make planetary climates less stable over geological time. Or perhaps life would find ways to adapt, as it so often does, turning apparent obstacles into opportunities. Our single-star system, by contrast, offers simplicity, a consistent source of light and heat, predictable days and seasons, a stable gravitational environment. These may be advantages for the development of complex life, or they may simply be the conditions under which we happen to evolve. The diversity of exoplanet discoveries extends to the materials from which planets are made. We are accustomed to thinking of rocky planets as being similar to Earth, with iron cores, silicate, mantles, and thin crusts of lighter rock. But the composition of a planet depends on the composition of the disk from which it forms, and that varies from star to star. Some planets may be carbon planets, worlds where carbon compounds dominate instead of silicon oxides. Such a planet might have a surface covered in graphite or even diamond, with hydrocarbon lakes and an atmosphere of methane and carbon monoxide. The geology would be utterly alien, with no plate tectonics as we understand it, and chemistry operating under different rules. Other planets may be ocean worlds with no solid surface at all, just hundreds of kilometers of water above a core of high-pressure ice and rock. Still others may be lava worlds, their surfaces molten from stellar heating or tidal forces, glowing with the heat of their own liquefied rock. Each of these possibilities represents a different outcome of the planet formation process. Each tells us something about the conditions under which planets can and do form. And each reminds us that Earth, with its specific combination of elements and conditions, is just one point in a vast space of possibilities. When we began this exploration tonight, we asked whether our solar system is rare. The answer, drawn from thousands of exoplanet discoveries, appears to be yes. But what does rarity mean in a galaxy of hundreds of billions of stars? Even if only 1 in a million stars hosts a solar system like ours, that would still mean hundreds of thousands of similar systems in the Milky Way. Even if only 1 in a billion, there would be hundreds. The universe is so vast that even extraordinarily improbable events happen countless times. The question is not whether other Earth-like planets exist. They almost certainly do. The question is how far apart they are, how difficult they are to find, and whether any of them have given rise to life and intelligence. We may be one of many, or we may be one of very few. The search continues, and with each new discovery, the picture becomes a little clearer. What has changed in recent decades is our perspective. Before the discovery of the first exoplanet, we could only speculate about worlds beyond our solar system. Now we have data, We have thousands of confirmed planets and thousands more candidates. We have begun to measure their sizes, masses, orbital characteristics, and even atmospheric compositions. This wealth of information has forced us to abandon our assumptions. We can no longer assume that other solar systems look like ours. We can no longer assume that the types of planets in our neighborhood are typical. We can no longer assume that Earth's conditions are common. The universe has surprised us at every turn. Hot Jupiters were a surprise. Super Earths were a surprise. Mini Neptunes were a surprise. The prevalence of tight-packed inner planetary systems was a surprise. The rarity of solar system analogues has been, perhaps, the biggest surprise of all. And this is how science works. We form hypotheses based on what we know. We test those hypotheses against new data. And when the data contradicts our expectations, we revise our understanding. Our understanding of planetary systems has been revised dramatically over the past 3 decades. It will likely be revised again as new telescopes come online and new detection methods are developed. What seems clear today may be overturned tomorrow, but for now, let us rest in what the evidence tells us. Our solar system's architecture is unusual, its stability is unusual, its combination of planet types is unusual, and the conditions it has provided for life on Earth may be more precious than we ever imagined. This preciousness is not cause for despair. It is cause for gratitude and responsibility. If we are rare, then what we have is worth protecting. If complex life is precious, then the biosphere we are part of deserves our care. The cosmos is vast and mostly empty. The distances between stars are immense. The silence of the void is profound. But here, in this small pocket of organized matter, something wonderful has happened. Life has emerged. Consciousness has awakened. And we, the products of 4 billion years of evolution on a rare and precious world, have begun to understand our place in the universe. Let this understanding accompany you into sleep. Let it deepen your appreciation for the planet beneath you and the sky above you. Let it remind you that every sunrise, every breath of air, every heartbeat is part of an extraordinary cosmic story. We are not separate from the universe. We are expressions of it. We are the universe experiencing itself, questioning itself, wondering at itself. And in this wondering, in this questioning, in this persistent search for truth, we fulfill our nature. We do what consciousness does. We reach outward, seeking to understand. The answers may take generations to find. They may take centuries. They may never come at all. But the search is worthy. The questions are worth asking. And the journey through the darkness and the light, through the silence and the wonder, is worth taking. So close your eyes now. Let the thoughts of distant worlds and strange suns fade into the quiet of approaching sleep. Let the vastness of space become a comfort rather than a fear. Let the rarity of our cosmic home become a source of wonder rather than anxiety. You are part of something rare and beautiful. You are a temporary arrangement of atoms that has somehow become aware of itself, situated on a planet that has somehow remained habitable for billions of years, in a solar system that has somehow avoided the catastrophes that have befallen so many others. This is your inheritance. This is your miracle. This is your home. Sleep now, beneath the same stars that have watched over our world since before life began. Dream of the cosmos and its mysteries, and know that when you wake, the great adventure continues. We are seekers. We are dreamers. We are the children of an extraordinary solar system, and the universe, vast and ancient and full of secrets, waits to see what we will discover next. Good night. Rest well, and carry the stars with you into your dreams.